So we also need to discuss what is the meaning of a filter generated by a subset. Okay, filter generated by a subset. So suppose B is a Boolean algebra and S is any arbitrary subset. In the proof of maximal implies ultrafilter, yeah, there was perhaps some confusion, right? So because we were using the filter generated by a subset. So here is the resolution. Yeah, I need to explain what is the filter generated by a subset. So one simple definition is you come from outside. Okay. So now S is a subset. Yeah, I mean I can say that this is my Boolean algebra. Here is 0, here is 1, and it spreads. So I am choosing a subset. I am choosing this element, this element, this element, and now I want to generate a subset using this, generate a filter using this. One simple thing is that I can always take the smallest filter which contains S. Now you remember that any arbitrary intersection of any arbitrary family of filters is again a filter. Yes, we proved that. So this is precisely that statement. I am saying that the filter generated by S is precisely this. It is the intersection of the family of filters which contain S. This intersection is always non-empty. Yes, what belongs there? The full, yes, the improper filter, the only possibility, the only improper possibility is the full filter, means the entire Boolean algebra. That is naturally a filter. I am not talking about a proper filter here. Yes, I am just talking about a filter. So the entire Boolean algebra is clearly contained in that collection. So the intersection, so if you put more elements, then the intersection will become smaller. Okay, you put more restrictions in S, the intersection will tend to be smaller. Okay, so it is the smallest filter containing S. However, what does an element of this smallest filter look like? Okay, so for this reason, now we are going to analyze this particular situation. So one thing, okay, maybe I will just consider a very simple example for now. What is the filter generated by a single element? So this is my filter A, this is my element A. What is the filter generated by A? What is the definition of a filter? It should contain 1, yes, it should be upset, right. So I need to close this under upsets first, right. So I need to consider everything that lies above it. I need to consider the upset. But what if I had another element B? Then for that also I need to consider the upward closed subset. So maybe I also close it under upper sets of B. So these are now two elements. However, I mean whatever I have drawn so far is the upper set of the set of A and B. I haven't done anything more. But there is a third condition in the definition of a filter. What does it say? It should be closed under meets, finite meets. So obviously I also need to close it under finite meets. Now here finite meet means, well, I can take this. This is my A meet B. But then again, once I have A meet B, I should again close it under upper set. Okay, so now I am considering this whole area. Okay. So close under, so we started with AB, we said take upper set, then we said close under meets, then what should we say further? Once we have closed under meets, should we say that close under upper sets, right? So you obtain some in between steps and then take upper set. Then again after taking upper set, should we say close under meets?
No,
it's already closed under meets, right? So this is the point where we stop, and this is what we call the filter generated by S. We do not have to go on indefinitely. Yeah, close under meets, then upper sets and meets and upper sets and meets and upper sets. No, we don't do that. Actually, only 2 steps are sufficient. First, close under finite meets and then take upper set. Only those 2 steps are sufficient, and for that reason, now read this statement. Each element of the filter generated by S is characterized as it is an upper bound of some finite meet of elements of S. Right? So by the property that there exists some finitely many elements S1, S2, Sn in S whose meet lies below A. So this is our filter generated by a subset. So when can you generate 0? Tell me in particular, when can you generate 0? Because I mean, so 0 will belong to this whenever, yeah, see, what is a lower bound of 0? 0. So you can replace this less equal by equality. So whenever 0 can be written as a finite meet of elements of S. Understood this part? Good.
Okay, so you have to show that for a Boolean algebra, a prime filter, a maximal filter, and an ultrafilter are the same things. And I've just written the definition of all 3 in case you forget them in the middle. So first, let's show that if you have an ultrafilter, then it's also a prime filter. So suppose that you have an element in F that you have written as X join Y. Then the definition of a prime filter would tell you that one of them belongs to F. So towards contradiction, assume that none of them belong to F. Now, since F is an ultrafilter, which was your assumption, you know that one of X, since F is an ultrafilter and X and Y don't belong to F, you know that their negations belong to F. And so their meet also belongs to F by the definition of a filter. And now, since X join Y belongs to F and this element belongs to F, you know that their meet belongs to F. So now you just use distributivity and you open it up, and you are using commutativity over here to get X meet negation X meet negation Y, and X meet negation X will give you 0. Similarly, here you will get a 0 because of Y meet negation Y, and now you're getting union of the join of 2 zeros, which is 0. But since F was proper, you know that this is a contradiction. Why is this a contradiction? Yeah, because if 0 belongs to it, then everything above 0 will belong to it. So this is a contradiction. What is this a contradiction to? It's a contradiction to our assumption that X does not belong to F and Y does not belong to F. So that means that one of them have to belong to F, which means, and since X and Y were arbitrary, you know that F has to be a prime filter. Any questions? Okay. Next, let's show that a prime filter is going to be a maximal filter in a Boolean algebra. Suppose that F is prime but not maximal, again towards contradiction. Then you know that since it's not maximal, there has to be a filter that properly contains F, call it F dash. and pick an element that is in f dash but not in f. This x is that element. Now, you know that 1 belongs to f because f is non-empty, and 1 can be written as x join negation x. And since you know that f is prime, you know that one of these has to belong to f, and you also know that x does not belong to f because that's how you picked x. Therefore, negation of x has to belong to the filter. And since negation x belongs to f and f is a subset of f dash, you know that negation of x belongs to f dash, and you also have that x belong to f dash. So their meet belongs to f dash, but their meet is 0. Again, you have a contradiction because here again your f prime is not proper, while you had assumed that this, well, you hadn't really assumed that it was proper. Yeah, this is not a contradiction. You have just forced that f has to be the entire algebra, and therefore f is not proper. And yeah, this is the definition of a maximal filter. Any questions? You have shown that if a filter properly contains f, then it has to be the entire algebra. So therefore, this is a contradiction. It's not a contradiction. This is the definition of maximality. Okay, so let's do the third part of the proof, where we show that if a filter in a Boolean algebra is maximal, then it's an ultrafilter. So as we have been going, we first assume that f is maximal, and then towards contradiction, assume that it's not an ultrafilter. Then by definition, there will be some element in the Boolean algebra such that that element is not in the filter and its negation is also not in the filter. And now we consider the filter generated by f and that single element x that we just picked. And since f is a proper, we call this new filter f dash, and since f is properly contained in f dash and f is a maximal filter, we know that f dash has to be the entire Boolean algebra. In particular, 0 belongs to f dash. And by the definition of generation of a filter that we just saw, x meet y is going to be less than or equal to 0 for some y in f. Now here, notice that we have chosen x to be one of the elements that we join with. Well, that is because if we had chosen some other element, say x dash inside our filter instead, then the meet of those elements would belong to f itself by the definition of a filter. And so,
talking about y instead of x?
No, I'm saying that if we had, so we know that this would be true for some x dash and y belonging to f union x, union singleton x. Now I'm saying that we can choose this x dash to be x itself, because if both of them were from f and not equal to x, then we would land inside an element of f itself by the definition of a filter. And so one of the elements in the meet is x, the other one is y, and by definition of generation of a filter, we know that x meet y is going to be less than or equal to 0 for some y in f, and since 0 is the bottom element, we know that x meet y is equal to 0. And we can do the same thing for negation x. We can find an element z in the Boolean algebra such that, in the filter such that negation x meet z is equal to 0. Now consider y meet z. Remember that y meet z is going to be an element of the filter since y and z both belong to the filter. This is equal to 1 meet y meet z, and we can just write 1 as x join negation x, and then we just use distributivity to open this, and we get these expressions. Now over here we know that x, we can use commutativity of the meet operation. Okay, in the second part we are using commutativity. Here we use associativity to conclude that since this is equal to 0 from the above, And since negation x meet y is equal to 0, again from our assumption, we get that this expression evaluates to 0. And since this element is supposed to be in F, we obtain a contradiction, since F was supposed to be a proper filter. And so we have finished the proof. This tells us that F is an ultrafilter. That is the assumption that is being contradicted above.
Okay, just now you have seen a proof that maximal, prime and ultrafilters in a Boolean algebra, they are all the same. Yeah? Especially we use the property that any proper extension of a proper filter, proper maximal filter, is everything. There is yet one more very interesting characterization of such maximal or prime filters, and that is using Boolean algebra homomorphisms. So please think about this particular shape. Yeah, I mean a Boolean algebra, I would like to think of it always as something like this. Yeah, it spreads. It has minimum, it has maximum, and then it has a spread. And usually the filters are somewhat like this. Yeah, the filters are the upper parts. And they are also closed under, like if there are two elements, then their meet is also there, right? So, in fact, this is also the shape of all the elements which should be sent to 1 under a Boolean algebra homomorphism. So, what I am saying, that consider this map from B to 2. B is the underlying set of the Boolean algebra and 2 is the 2-element Boolean algebra, 0 and 1. So, whenever we have only 2-element Boolean algebra, then we can talk about a function as a characteristic function, right? So, therefore, I am saying that if f is a prime filter, then K-F is a Boolean algebra homomorphism, and conversely, if I have a Boolean algebra homomorphism, then the inverse image of 1 under that homomorphism is a prime filter. Okay, so let us try to prove this. This is also quite easy. All of these proofs are very simple. You just follow your nose, follow the definition. So, suppose f is a prime filter, then we have to show that it is a Boolean algebra homomorphism. So, then sorry, I should use black color. Then 0 doesn't belong to f, correct? Because it's prime, so it's proper. So, therefore, what can we say? 0 doesn't belong to f. So, what is the value of K-F at 0? 0. Okay. So, you needed for a homomorphism 0 should map to 0, right? 1 belongs to f because f is a filter, therefore K-F of 1 is equal to 1, right? Then suppose now we want to show that take two arbitrary elements, suppose xy be in B, then x meet y is in f, yeah, x meet y is in f if and only if what happens? See, if x meet y is in f, then x is an upper bound of x meet y is an upper bound of x meet y. So, therefore, x belongs to f and y belongs to f, correct? However, because we are working in a filter, if x belongs to f and y belongs to f, then x meet y also belongs to f. So, this condition actually became if and only if, right? So, now this property happens if and only if what happens? K-F of x meet y is equal to 1, and this happens if and only if chi f of x is equal to 1 and chi f of y is equal to 1. Okay. Now, when is the meet of two elements equal to 1? When they are both 1, yeah, because you remember the truth table. Truth table says that conjunction, like meet of two things, is true if and only if both of them are true, right? So therefore, if and only if chi f of x meet y is equal to 1. Yeah, if you are not convinced, please think about it again. So therefore, we have, I wanted to say that their meet is 1. So what did we show? Chi f of x meet y is equal to 1 if and only if chi f of x meet chi f of y is equal to 1. So this is 0 if and only if that part is 0, that is the definition. So therefore, both these values must be equal. There are only two values. So therefore, chi f of x meet y is equal to chi f of x meet chi f of y. Okay, so this is the third property. What is the meaning of a prime filter? Prime filter is same as ultrafilter. So let's prove that. Right. So suppose x belongs to B. Then x belongs to F. If and only if, what happens? Negation x is not in F. Yes, because prime is same as ultra. Okay, x belongs to F if and only if negation x is not in F. Now x belongs to F if and only if what happens? Chi f of x is equal to 1. Okay, if and only if chi f of negation x is equal to 0. Are we done? Are we done here? What do we need to show? Negation chi f. Yes, negation chi f of x is equal to chi f of negation x. Yeah, this is what we needed to show and we are done here. Okay, I have shown one side. Please complete the other side. You just have to use the definition that homomorphism is a map which preserves 0, 1, join, meet, and complements. Yeah, and then conclude something about the filter side as well. Okay.